Today, we are jumping into a real classic, an absolute gem in the world of algorithms, Kadane's algorithm. It's the famously elegant and, incredibly fast solution to a problem that pops up all over the place, from coding interviews to analyzing real-world data.
So, let's make this real. Imagine you're looking at a stock's performance. Some days it's up, some days it's down. What you want to find is that one single continuous stretch of days that would have netted you the biggest possible profit. That right there, that's the core of what's called the Maximum Subarray problem. Now, what's the first thing you'd think of doing? Probably the brute force way, right? Check day 1. Then check days 1 and 2 combined. Then days 1, 2, and 3. Then start all over again at day 2. You can see how this gets out of hand. With thousands of data points, this approach is just painfully slow. There has to be a smarter way.
And that, my friends, is where the genius of Kadane's algorithm shines. It solves this whole puzzle by looking at each number in the list exactly one time. That's it. No going back, no complicated loops, just one clean, efficient pass.
The logic at its heart is just beautiful and simple. At every single number, we make a choice. Just one of two things. Option 1, we keep building on what we have. We extend the current subarray by adding the new number to our running total. Or, option 2, we decide that what we've been carrying is just dragging us down. Maybe the sum went negative, so we ditch it. We start fresh with a brand new subarray that begins with the number we're on right now. That's the whole decision process.
So to make that decision, we just need to keep track of two little variables. The first one, let's call it maxEndingHere. Think of this as the algorithm's short-term memory. It's constantly updating, always telling us, what's the absolute best sum I can get for a subarray that ends at this exact spot? And the second variable is maxSoFar. This is our long-term memory, our grand champion. While maxEndingHere is going up and down with the flow of the numbers, maxSoFar is just watching. It only cares about one thing. What's the highest value maxEndingHere has ever reached? This is the one that's going to hold our final answer.
Okay, theory is great and all, but let's actually see this thing in action. We're going to walk through an example array together and watch how these two variables play off each other to find the answer.
All right, let's trace this. We start with the first number, 2. Simple enough. maxEndingHere is 2, and maxSoFar is also 2. Now we move to 3. We ask the question, is it better to add 3 to our current sum of 2, making 5, or just start over with 3? Well, 5 is obviously better, so maxEndingHere becomes 5, and maxSoFar updates to match it. Next up, -8. Adding that to our 5 gives us -3. So maxEndingHere is now -3. But look, maxSoFar stays put. It remembers that 5 was the best we've seen. Now here's the magic moment. We get to 7. Do we add it to our current -3 sum? That would give us 4. Or do we ditch that negative baggage and just start a new subarray with 7? 7 is way better. So we start fresh. maxEndingHere resets to 7, and maxSoFar sees this new, better value and updates to 7. That's the key decision right there. From here, the process just keeps on rolling. And after that one single pass, after looking at every number just once, our maxSoFar variable is holding the final answer. And that answer is 11. And where did that 11 come from? Well, it corresponds to the subarray that began right when we made that crucial start fresh decision at the number 7. The winning streak is 7, -1, 2, and 3. So, we've seen how it works. Now let's talk about why this algorithm is such a powerhouse, why it's the go-to solution in terms of pure performance. Believe it or not, that whole extend versus start fresh logic we talked through, it can be boiled down to this one single beautiful line of code. All it's saying is the new maxEndingHere is going to be whatever's bigger, either the new number all by itself or the new number added to what we had before. It's so simple, but so powerful.
And that simple logic delivers an absolutely massive payoff. Look at this comparison. The brute force method, that O of n squared one, gets slow really fast. A smarter divide and conquer approach is better at O of n log n. But Kadane's, it's O of n. That's linear time. It means the time it takes is directly proportional to how many numbers you give it. You literally can't do better than that. And it uses basically no extra memory. It's just optimal.
Okay, so because it's so clever and efficient, you can bet you'll see Kadane's in technical interviews. So let's quickly run through what you need to know to absolutely nail it.
You know what really impresses interviewers? Thinking about the weird situations, the edge cases. For instance, what if every single number in the array is negative? A good implementation of Kadane's correctly finds the single largest number, which is the least negative one. What about an empty array? You'll have to clarify what they want, but usually the answer is just 0. And if you're dealing with potentially huge numbers, you gotta be aware that the sum could get too big for a standard integer. Mentioning you might use a larger data type is a huge plus.
So when you're in that interview, here are your key takeaways. Don't just write the code and walk away. Talk through the logic. Explain the difference between the local max, maxEndingHere, and the global max, maxSoFar. Be proactive. Bring up those edge cases we just talked about. It shows you're a thorough and careful programmer. And showing you're aware of things like overflow and are ready for a follow-up question, that's how you stand out.
And speaking of follow-ups, let me leave you with a classic one to chew on. You've totally nailed how to find the best streak in a straight line, but what if that data wrapped around? What if the last day's performance could connect back to the first day's? What if the array was a circle? The solution actually builds right on top of Kadane's, and it's a fantastic next puzzle to explore.